Good morning, everybody. My name is Vance Kite. I am a doctoral candidate in the Department of STEM Education at NC State University. This presentation was prepared for the annual meeting of the National Association for Research in Science Teaching, and the title of our presentation is Secondary Science Teachers' Conceptualizations of Computational Thinking and Perceived Barriers to CT Content Integration. This was prepared in conjunction with my advisor, Dr. Soon-Hae Park. So to kick us off, our work is motivated by the following assertions. First, that CT proficiency is foundational to both 21st century employment and democratic participation. That exposing the broadest possible range of students to CT requires that CT be integrated in core classes. Achieving CT content integration depends upon teachers who understand CT, where CT fits in their curriculum, and how to implement CT-infused curriculum in their classrooms. Preparing teachers to implement CT-infused curriculum is dependent upon creation of CT-PD that addresses teachers' alternative conceptions of CT and their perceived barriers to CT integration. And to date, only 4 studies have been conducted to understand either teacher CT conceptualizations or perceived barriers to CT content integration. Our work is guided by the following research questions. First, what is the nature of secondary science teachers' conceptions of computational thinking? Second, what barriers to integrating CT with existing science curriculum do science teachers perceive? With regards to a theoretical framework, we draw on the work of Frelon et al. And their ICILS CT framework, which was developed to create CT assessment items for the 2018 ICILS study. They define computational thinking as an individual's ability to recognize aspects of real-world problems which are appropriate for computational formulation and to evaluate and develop algorithmic solutions to those problems so that the solutions can be operationalized with a computer. The thing that I like about Frelon's framework is that they divide computational thinking into 2 phases. First, conceptualizing problems, which involves knowing about and understanding digital systems, formulating and analyzing problems, and collecting and representing relevant data. And then with a firm understanding of the problem in mind, they move towards operationalizing solutions through planning and evaluating the solution and then developing algorithms, programs, and interfaces. Methodologically, here's how we went about our study. It is a survey study, so we developed a survey that consisted of 17 items. For the purpose of this paper, we report on 4 items. We sent the survey out to 1,001 secondary science teachers across our state. For this presentation, we focus on the data from 4 questions. Have you heard of CT? Have you had CT-PD? How would you define CT? And then select your 3 biggest barriers to integrating CT with science content. For that question, we had 9 literature-supported barriers to CT content integration, and teachers were allowed to select 3 of them. We received 123 completed surveys. Our participants were 79% white, 72% female, 55% of them had 6 or more years of experience, 58% taught in high school, the rest were in middle school, 52% taught in rural areas. 8% of them reported having had CT-PD, 46% reported having heard of CT, and 54% had not heard of CT. To analyze the data, we used qualitative content analysis using the constant comparative method. For research question 1, this resulted in 34 open codes that were synthesized ultimately into 7 categories. And for research question 2, we used frequency counts of the number of times each barrier to CT content integration was selected. All right, let's take a look at our results for research question 1. How do secondary science teachers conceptualize CT? I'm going to put a key up here for the diagrams or for the graphs that are going to be coming up. So with regards to the colors, each color represents one of the major themes that came out of our analysis. Dark blue refers to the theme of a specific way of thinking. Then solving problems with computers or specific CT practices, general problem solving, connected to teaching, or relating to math or data. For all teachers, here's what the graph looked like. So when asked, how would you define computational thinking? 39.5% of all of the quotations defined CT as a specific way of thinking. 25.8% defined it as solving problems with computers or specific CT practices. 15.3% spoke about it in terms of general problem solving. 9.6% connected it to teaching, and just under 5% related it to math or data. Now we're going to look at the three different buckets of teachers individually. For those teachers who had not heard of CT at all, here's how they defined computational thinking. 46.6% of them referred to it as a specific way of thinking or defined it as a specific way of thinking. 8% defined it as solving problems with computers or specific CT practices. 5% spoke about it in terms of general problem solving. 5% connected it to teaching, and 35% related it to math or data. For teachers who had heard of CT but not had professional development in CT, they defined it as follows. 28.9% of them talked about it as a specific way of thinking. 30.4% said solving problems with computers or specific practices. 20.2% spoke about it as general problem solving. 13% as connected it to teaching, and then 7% related it to math or data. And then for our final set of teachers, which are those that had professional development about CT, they defined computational thinking as follows. So 60% of them, or 60% of their quotations, wrote about it as solving problems with computers or specific CT practices. 10% as a specific way of thinking, 20% as general problem solving, 10% as relating to math or data, and none of them said that it was a method of teaching. All right, if we look at the most frequently used codes and divide the teachers up into two buckets, all teachers and then just the teachers that have had CTPD, the most frequently used codes were as follows. So if we look at all of our teachers together, the most predominant codes were thinking like a computer, logical thinking, and mental calculations, and all of these were in that theme of a specific way of thinking. If we look at our teachers who had CTPD, their most frequent codes were a canonical definition, which means that they provided a definition that is in line with academic literature about what CT is, or they talked about PRADA to solve problems. That would be pattern recognition, abstraction, problem decomposition, and algorithms to solve problems, and solving problems with computers. Now, if we consider our first research question in the light of Frelon's framework that I spoke about earlier, and look at all of the quotations we have, 72% of the quotations were not aligned with anything that Frelon would consider to be computational thinking. 28% of the quotations were aligned with Frelon's conceptualization of CT, and most of the quotations that were aligned with Frelon fell under the categories of solving problems with computers or relating to math and data. If we look at the percent of quotations aligned with Frelon between our two buckets of teachers who have had CTPD and those that haven't, 70% of all quotations from teachers who have had computational thinking professional development were aligned with Frelon, whereas only about 20% of teachers who had not had CTPD aligned with what Frelon says CT is. And then finally, if we think about Frelon in terms of those two phases of conceptualizing problems and operationalizing solutions, 89% of the Frelon-aligned quotes referred to operationalizing solutions, while only 11% focused on conceptualizing problems. All right, with regards to the barriers that teachers perceive to integrating CT with their content, this would be research question 2. I start with the following key. So our 9 barriers were: I don't understand CT, my students aren't prepared for CT-infused curricula, I don't understand how CT aligns with my content, I don't have access to the necessary technology, I don't have room in my curriculum, I'm not comfortable with technology, other that allowed for some text entry, lack of support from administration, and I don't think CT will benefit my students. If we look at all of our quotations together, here's how they break out. The largest proportion of quotations, or not quotations, but selections, where I don't understand computational thinking, followed by my students aren't prepared for CT, I don't understand how CT aligns with my content, I don't have access to the necessary technology, and then on down the line. So as you can see, the three biggest barriers by far where I don't understand CT, and then my students aren't prepared, and I don't understand how it aligns with my content. If we again break our teachers up into two buckets, teachers who have not had CTPD and those who have, the ones that have not had CTPD, their graph closely mirrors the one for all teachers because there were so many teachers who had not had CTPD. So far and away, the most dominant barrier to integrating CT was that they don't understand CT, and then my students aren't prepared for CT, and I don't understand how it aligns with my curriculum. For those who have had CTPD, we find that their graph looks differently. For them, not understanding CT was much less of a problem, though there were 3 of those teachers who said that they still didn't understand CT enough to integrate it in their curriculum. But for these teachers, the other big problem, or the other major barrier that they cited, was that their students were not prepared for CT-infused curricula. We also see other and that focused on teachers writing about not having time to plan CT-infused curriculum. We also see that for these teachers, not having room in their curriculum was cited as being a major barrier to integrating CT with their curriculum. All right, let's go through these things in terms of discussion. So for research question 1 about how secondary science teachers conceptualize CT. So our findings align with the work of Sands et al. And Ling. Both of these were studies about teacher conceptualizations of CT, and that our teachers also frequently equated CT with doing math and solving problems. However, unlike the other 2 studies, they rarely provided a canonical conceptualization of CT. If we consider our study and similar works that consider teachers' conceptualizations of CT in the light of Frelon's framework, we find that teachers focus predominantly on operationalizing solutions and rarely on conceptualizing problems. Conceptualizing CT as thinking like a computer seems to be a common misconception about the nature of CT. It was one of the most common quotations that we saw in that question about defining CT, and is explicitly not aligned with academic definitions of computational thinking. Wing herself specifically said that CT is human thought, not computer thought. And CTPD does seem to be effective for moving teachers towards CT conceptualizations that are more aligned with those of the academic community. For research question 2 about the barriers to integrating CT, we highlight that a lack of CT understanding is a dominant barrier across all groups. We even saw it in those who had had CTPD. This is problematic because low understanding leads to low self-efficacy with integrating CT, which would hamper CT integration in the classroom. Given that 30% of CTPD teachers identified lack of CT understanding as a barrier, research is needed to identify CTPD design elements that enhance the durability of the program's content. The prevalence of teachers' belief that their students are not academically prepared for CT-infused lessons is concerning because teachers believe mediate their practice, meaning that these teachers would be unlikely to bring CT-infused lessons to their students. The implications that we draw from this work are as follows. CTPD designers can expect that most teachers attending their program will have very little knowledge of CT and will initially view CT as logical thinking like a computer, or relating to math or data. So these misconceptions or alternative conceptions can be used in the design of the CT programs. CTPD designers should place equal emphasis on supporting teachers in conceptualizing problems and operationalizing solutions rather than just operationalizing solutions. The frequency with which teachers cited a lack of CT understanding as a significant barrier to implementing CT is a clear call for broad creation and dissemination of CTPD. CTPD programs should focus on helping teachers overcome the belief that CT isn't for their students and show teachers how CT fits in their curriculum. And finally, CTPD scholars must seek CTPD design elements that will increase teachers' CT integration, self-efficacy, and increase teachers' retention of the program's content. With that, we conclude with our references. I will note that this presentation is part of a larger study. Hopefully the full paper will be headed out for review sometime in the summer. If you have any questions, feel free to shoot me an email. My email is vkite@ncsu.edu. It's also on the first slide of the presentation. Thank you for the time you took to listen to our presentation, and have a good day.